The floor is yours.
Thanks. Assalamu alaikum. How are you? Ready for the second part? So let's start inshallah today. Warming up exercise. Surprise quiz for you. Okay, it's just to show how you got from last time. It's not a formal quiz. Quiz that we will all solve together. So here's the problem that we talked about last time, right? The age prediction. We have 3 versions of it, and the question is, what is the type of the problem, of machine learning problem, for each version? Okay. So the first version, if we are predicting the age of every person, what is the type of that problem? What's the type of machine learning problem here? Do you remember the types? What were the types? Huh? Supervised, unsupervised, and reinforcement learning. Okay. And under supervised, we discussed 2 types or subtypes: classification and regression. Yes. Okay. Right. For this, which type is that? Raise your hand, please. Where is Mukartum today?
I asked her specifically to come.
We'll see. She doesn't, of course. She doesn't need to come. Okay. I thought that you don't need to come.
No, I don't know that with her we cannot proceed.
Okay, so what is the type here? Raise your hand, please. What's the type of that problem? Okay, we'll wait until you answer this question. We'll stop the workshop. Raise your hand, please. I want to see hands. Yes, please. Supervised. What type exactly? Classification. Okay. Any other? If you are predicting the age, then this will be classification. What are the classes here?
It's the range of the age.
I didn't say the range yet. Okay, I said the age itself. Forget about what is written there. Okay, but if we are predicting the age itself, what should be the type of the problem then? Is it still classification, you think? No. So what is the type? Regression. Because we are trying to get a value. Okay, so there's no classes here. We are trying to get a value of the age, right? So this is then a regression problem. How about if we are predicting the range now? Is it classification now? What are the classes? The ranges, right? Different ranges. We can say kids, youth, and so on. Okay, or we can identify the ranges like that. So in this case, it will be, we have multiple classes, and it will be a classification problem. Okay. Now forget about the age. If we are trying to predict similar people from their faces. Huh? Unsupervised. Okay, and what is the name of that problem specifically? Clustering. Who said clustering? Yes. Okay, so in this case, because we are trying to find who are the similar people, just based on their faces, so we are clustering them, so this is a clustering problem. Okay, is that clear? So this is an example of regression problem. This is an example of a classification problem, and both are supervised. And this one is not supervised. We don't need any label here to group people together based on the features of their faces. Okay, if they look similar, then they should be in the same cluster. Okay, regardless of the difficulty of the problem, but these are the types of these problems. Okay, any question about that? Okay, so let's move on today. I remind you with this roadmap. This is the roadmap of the entire workshop, but we are done with the first part, and today we'll focus on this only, inshallah. Hopefully that we'll have time. We'll talk about some evaluation issues, not completely on evaluation, but some issues with evaluation. And then we'll talk about a brief introduction to neural networks. Then briefly we'll talk about how we see machine learning in a full pipeline, in a real problem, real life problem. And then what is the differences between AI, machine learning, and deep learning. And then we'll give you some pointers for more information. Okay? So that's the roadmap for today. We'll start by evaluation. First, what do we mean by evaluation, the word evaluation? Do you have any idea? Have you heard about this word before? Evaluation. Measuring the performance. Okay? measuring the performance. Why do we need to measure the performance in this case? Because that's very important, right? We don't want just to build a model, okay, without knowing how good it is. Okay, so the evaluation is about how good the model that we trained or what that we built is in solving that problem. Okay. You remember that we discussed about decision trees last time, right? Now assume that we have learned a tree, like what we did last time, and we assume also that it fits the training data perfectly, which means that if I tried every single example in the training data, tried to predict the label for it using the tree that we built, assume that we got perfect results. We are really classifying every example in the training data perfectly, accurately. We didn't get any error. Okay? The question is now, are we done? Is that the best we can do?
No.
Okay? Can we guarantee that we have found the best or very good model?
No.
Why not?
Because as you mentioned last time, that if the doctor give us the example in the class and ask us the exam, same as the example that give it to us.
Yes.
So if
Doesn't mean anything.
doesn't mean anything.
Doesn't mean anything because we are just memorizing what we saw, right? So that shouldn't be the focus. Okay. So the goal is not to check the training error or the training accuracy. Training error is not sufficient to know whether the model that we built is really good or bad. Okay? Because it might happen that the model memorized every example. Okay? So that's not the real test. Okay? So a tree can classify every data perfectly, but if I give a new examples to the decision tree that we built, it might give some errors, right? It might make mistakes in the decisions. Okay? And this is the concept that we discussed last time and emphasized on it, right? That we don't care much, of course we care, but don't care much about what we do in training in terms of perfect prediction of all the training examples. We care about generalization. Okay? What do we mean by generalization? The performance when the model that we learned sees new examples that it didn't see before. Okay? That's what we care about. Yes, we train a model, but we don't want to train it in a way that it will do very bad when it sees unseen examples, when it sees new examples, when it gets new examples. Okay? We want it to be good in training, which will be a good indication for the testing error, but we also care much about testing error, about error or accuracy of the model when it gets new examples that it didn't see before in training. Okay? Let me show you 3 examples. Let's say that here we want to classify between the blue circles and the red crosses. Okay? So what type of problem is that? Classification, right? We have 2 classes, A and B, and we want to classify between them. Okay? And let's say that the classifier is represented by this blue curve in these 3 cases. Okay, so we have 3 classifiers. This is 1, that's 2nd, and that's the 3rd. Which one of these is the best? It depends. It depends. It depends on what? There's other Kalsum here? Why are you? Anyway. Okay.
The last one is complicated. It's perfect, but it's complicated.
Okay, fine. Our life is very complicated, right?
Yeah, but
You don't think life is very complicated?
the person depends on the person's accuracy you want the model to be.
But you said it's complicated, right?
Yeah.
Okay, why is the complication bad here?
It's hard to implement. Yeah.
Hard to implement? No. It's not hard to implement at all. It's not harder than the others.
Maybe
Don't worry about that.
the first one is linear.
Okay, and linear is good or bad? Huh?
Linear.
Good. Okay, so Mukalthum, remember, Mukalthum said this is the best, or you didn't say this is the best.
Yeah.
You said there is a problem with that. So which one you said it's the best then?
It depends. I say.
Kulsum because the wisdom is really high. She doesn't want to confuse us. Okay, so just oversee what is going on in the class. Yes. What is the best? The first one. Okay, why is that? Okay, right. You see that the three are really different, right?
Yeah.
Okay. The first one, in terms of training, it's not getting very high accuracy, right? There are some. If we say that this side is the red side and this is the blue side, still there are some examples that are not perfectly classified.
But we can
Right?
say that this will work with more systems. Yes.
We'll get to that. Okay. So this is the case here. We have some errors, right? Here, it seems like we have less errors, right? We have less errors and seem like this is capturing the blue class much better than this, right? Here, we are getting no errors at all. Okay, the curve here is really perfectly distinguishing between the two classes, right? Right? So based on that, which one is the best? The last one, right?
No.
Okay. So the answer is this one is really bad. Okay. Why is that? Because it looks like it is learning even noise in the data. Okay. So let's look at let's look at these two examples. Okay. If you look at the data without looking at the blue curves, you might think that, oh, it looks like these two samples are really noisy. They might not be actually red. They should be blue. And maybe because of some problems in getting the data, we thought that they are blue, but they should be actually red. Okay? They look like outliers here. Okay? It might not be the case. Okay? It might not be the case, but they look like outliers. This one actually learned the outliers, learned the noise, that this is part of the red class, although most probably it's not. Okay? So this one is generalizing better. This one is expected to do better in when it gets examples that it didn't see before.
Which one?
This one. Okay? So in this case, we call it overfitting. It fits the training data very well, but most probably it will really do bad when it gets new data, because it's putting very much attention to very small details in the data. Okay, it doesn't generalize. Type. Okay, we maybe yes.
Sorry, I have
Yes.
maybe we are interested in more accuracy, but we don't criticize the data. So
Very good.
The data is clean.
Okay, very good. What you see here is the accuracy of the training data. On training. We didn't see the accuracy on testing data yet.
Maybe it is also good on whenever it goes to real life if the data is so clean.
Very good. Okay, very good. And that's why we will do something to see whether it is really good or bad. But that's an example of putting a lot of attention to small details that might not be good in real life. Okay? So we call that overfitting. If you didn't understand it very well, I will give you another example and I think it might be even more clear. This one is called underfitting. Okay? It generalizes much more than we need. Okay? And this one is probably fitted. Okay? So we call this overfitting, we call this underfitting. Now the other example that I think will be more clear is the analogy between learning and getting back to the example that we discussed last time, which is student course understanding. Okay? If you have, let's say, machine learning course and you will be examined at the end. Okay? Overfitting is when you memorize all the examples that the teacher gave you in class. Okay? Your classifier will be perfect on anything that the instructor gave you in class. Okay? Very well fitted around all the problems that you saw before. Okay? Underfitting is when you don't study at all. Okay? You don't care about the exam, and inshallah will be good in the exam. Who knows? We do that all the time. Of course not. Okay? So you don't study at all, and you try to do something in the exam without studying at all. This case is when you study, you understand the concepts without memorizing the exact examples. Okay, you understand how the problems were solved. Okay? You might not get all the examples in class perfectly, but you will probably do better in the exam. Okay? So you got the idea now? Okay. So this is called overfitting, and remember always that overfitting is like memorizing. We just memorize. When you see this example, this is the class. This example, this is the class. Okay? In classification. Okay? But the better way is to try to generalize, not to fit to probable noise in the data. Okay? So the solution to that is not to only look at training error. So we are looking here at training error. This is the best training error ever we can get, right? 100% accuracy on the training data. Okay? This is much worse than this one, right? So in order to see which one is really better, we have to set aside a set of examples. We call them test set. Okay, so we discussed about training set or training examples. There is another set which is called testing set. Okay, and the testing set has to be really different from the training set. Okay, so the rule here is that you should not look at this testing set while you are training. Okay, and looking here has two meanings. While you are training, you don't have access at all to the testing set. Okay, because this is the set that you will use to really examine the model that you are building. Okay, it's like the exam. You don't see the exam, the final exam, right, while you are studying. Okay, and the other thing is that I'm really literally mean touching and looking. Okay, you don't even look while as a user and as a human while you are training your example, your system. You should not look at you as a human, not just the system. You should not look at the testing set. Why is that? And okay, the system will not have access to the data, to the testing data. You understand that, right? But why should the human himself not? He should not look at this testing data. Yes.
Because again, maybe the overfitting problem happened.
Okay, but the system is trained, right?
But it may affect our
How?
decision.
How?
When we look at to the overfitting, or look at to the testing data, when we want to build up our model, it may affect that one.
The humans are very good learners, right? If you look at the test data, you will learn something from the test data, and you might be tempted to reflect that in your model. Okay, so you will be affected by what you see in the test data. Now it's kind of cheating, right? It's like you know some problems that you will get in the exam, okay, while you are studying. So you will be tempted to really solve these problems. Make sure that you solve them right. Okay, so this is now very clear that we should not, or we should never ever touch our test data. Okay, if I found bigger warning sign, I would have put it. Okay, so this is very important rule in machine learning, in training any system, that you should separate the training data from testing data. They should not overlap at all, and also you should not look at the data, at the test data at all. Okay, so this means that you will train your data, your model on training data. You get a model, and then you test it on the separate test set. Okay? Yes.
Don't we choose our testing data?
Do we what?
Don't we choose our testing data as well?
Don't we reuse?
Don't we choose the test data?
Choose. Okay. Good question. Usually we have, let's say for classification, just to be simpler, let's say that we have a set of labeled data already. Okay, we have images with their ages, people with their ages. Okay, what we should do is to randomly choose some of them to be the training set and some of them to be the test set, randomly. Okay? Usually the percentage is like 80% training or testing. 80%, 20%. 80% training and 20% testing. Okay? Usually we have this. There is something called cross validation, but that's beyond the scope of this workshop. But it is the same idea that we should split our training and testing. Okay? Is that clear? So remember this warning sign. Regarding the question that Dr. Nizar asked earlier, to avoid that, we usually change the model, the parameters of the model, and we plot both training and testing accuracy. Okay? So we see that with some parameter, with some values of the model, we are getting better in terms of training and testing, right? So that the accuracy of the model is getting higher, and the accuracy of the model on the testing data is getting also higher, until we have something here, after which the performance for training data will continue to increase, but the performance on test data will decrease. So what's happening here? Overfitting. So what happened here is that we have an overfitting case here. Okay? We overfit the training data, but now the model is not able to generalize to test data. Okay? So what should we do then?
We take to the range, this range only.
What?
Should we like just take this range?
Yes, so we should stop here.
Yeah.
Okay? We should pick the value of the model at that point. Okay? Although at that point the training error is much less, the performance of training is much higher. Not much higher, but it is higher. Okay? But we don't care much about the training accuracy as we care about the testing. Okay? So is that clear now? Okay. So I hope that you understood now what is the difference between overfitting and underfitting, and why we should have something called training data and testing data, and how we should deal with each of them. Okay? And that's enough for me in terms of evaluation. Just as an example in decision trees, if you think about what we discussed last time, if we build a full tree, we continue to the branches so that we really stop only with the conditions that we said last time, it will be a tree that memorizes every example, almost perfectly classifying all examples. This is now a kind of overfitting. What we do to avoid overfitting with decision trees is to stop at some depth. We will say all branches, all branches in the tree will not be more than 3 nodes or 4 nodes. Okay, it's like cutting the long branches from the tree. Okay, and this showed by experiments that it gives much better performance on testing data. So it is more general than really memorizing everything in the training. Okay. This is just an example in the context that we discussed before. Any questions up to this point? Because this is ending now this part of the talk. Much slower than I expected. Any questions? Okay, now we'll switch to the second example of classifiers, which is neural networks. Okay? What was the first example? Evaluation. What was the first example of classifiers that we discussed? Huh? I don't really hear. Tree diagram. Decision trees. Okay, so decision trees was the first example of classifiers. Okay. So neural networks. From the word we have neural, right, and networks. And it is really, the model of neural networks was inspired by what is going on, or what we think is going on in our brains. Okay? So the story, in short, is that our brain is composed of a bunch of units called neurons. Okay, so this is a model of a neuron. Neurons connect to each other, and they communicate through signals between each other. Okay, so there are connections between different neurons, and you communicate by sending signals. Okay, and we say that a neuron fires or has or is activated. Okay, when it has strong signals from the neighboring neurons, and also strong connections. Okay, so both. Okay, so the one neuron, one cell, will be activated when it has it's receiving strong signals from other neurons through strong connections. Because if the connection is really weak, it doesn't matter if the signal is really strong or not. And if the signal is strong, it does, no. If the signal is weak, it doesn't matter the strength of the connection. Okay? Okay, so that's what we think is happening in a very short definition. And once the neuron is activated, it sends its activation signal to the other neurons that it is connected to, okay, through these terminals. Okay? Now this idea inspired the work of neural networks, because now we can think of that cell, okay, and have a mathematical model of it. Okay? So in this model, let's say that this is the neuron, and as we said that the neuron is activated getting two things, getting signals from other neurons and through connections. Okay? Let's say that the values of the activation of other neurons are x1, x2 up to xn, and the strength of the connections will be modeled by what we call weights. Okay? Each connection has a weight. Okay? And what is happening is that the neuron aggregates the values that it is getting, okay, and produces what we call a weighted sum. So the weighted sum is very simple. It is the multiplication of each signal by the weight of the connection that it is connecting to the neuron, and that's the sum of that. Okay? So it will be x1 times the w1 plus x2 times w2 and so on. So that's the weighted sum. Now this is the signal that it is receiving. If that and just as a mathematical model, okay, we also add what we call bias to the model, so that the model will be more flexible. We can talk about that later. Okay, but let's assume that there is another weight here called bias. What is happening is that this value of bias is added to the sum, but what decides whether that neuron will be activated or not is the following element. Okay, so we have something like a step function here, that if that sum is positive, then the neuron will produce a signal of +1. Okay, if it is negative, then the output signal will be -1. Okay, so that's the model of the neuron. Of course, the neuron doesn't do exactly this. Okay, but that's a mathematical model of the neuron. Okay, so again, we have for that neuron we have signals from the neighbors, and each signal is going through a connection. Each connection has a strength which is modeled by the weight, and we sum over these weight signal multiplications. We add a bias, and then we see whether this summation is, which we call it z here. If z is greater than 0, then the neuron will fire or will be activated, and will be -1 if it's not. Okay? Is that clear? So this is a model of one neuron. Yes?
So what does that exactly represent?
Very good. Okay? It represents a neuron, but by itself, of course, it's not the brain yet, or it doesn't look like a brain yet. It's just one cell of the brain. And of course, we don't know even if it's very accurate or not, because we don't know yet what is exactly happening. Okay, but that's just a rough model of what one cell is doing. Okay, now let me try also to answer your question in a different way and says why we are modeling it that way and how is that related to learning. Okay, there is a theory that that says that learning in the brain is by learning which neurons should connect to each other and how much. Okay, and we have millions of neurons in our brain, not just one. Okay, some of them are connected to others and some are not. Not every neuron is connected to every neuron. Our knowledge that we learn, the theory says that the knowledge that we have in our brain is encoded by the connections, whether they exist or not, and how strong they are. And that changes over time. Okay? New connections are built, new connections are removed, connections are getting stronger, connections are getting weaker, and that's the knowledge that we have in our mind. I'm not saying this is the reality, but that's the theory behind that. Okay? And this is actually reflected in what we will see. That now, where is the model? We call what we called model before. The model will be these weights will be represented by these weights and this bias. The values that that shows how strong the connections are to the neuron. Okay? And one thing that I didn't mention is that now to model this as a machine learning model, we will assume that these are not actually neurons, these are just the input features. You remember the decision tree example when we saw the training table? Right? We had features, right? The outlook and windy and the wind and so on, right? These are features. Okay? So we'll assume that these are the features, the feature values. Okay? And we want to learn weights so that this neuron will produce 1 if that example is belonging to class A, and -1 if that example is belonging to class B. Okay? So this is the idea here. We want to find the weights that will allow us to really do the classification with a good accuracy. Okay? And this is how we think, or the theory thinks, or the theory says how learning in the brain is done. Okay, is by finding the right weights or changing the weights. Of course, it's not that simple. Okay, but this is just a rough model. Okay, and this is now we can look at it as the neuron that we are modeling. These two together is the neuron. The summation and the step function that is applied to the weighted sum. Okay? It is very important to understand this because based on that is everything else in neural networks. Okay? So this is the model of one neuron. We have input features here. We have weights. The weights are the input the values of the features are weighted by the weights and then summed together, and then the sum is going through the step function to decide if the sum is positive, then the +1 will be produced. If negative, then -1 will be produced. Okay? We call this model perceptron. One node only. Okay? And that algorithm was really old. Okay? That only represents one neuron. This is called perceptron. And now I merged together the summation and the step function just to show you that now it is one thing and it is called perceptron. So nothing new here except that now we have this name. As I said, where is learning? Here. The model itself is the set of weights. This is what we want to learn. Do you remember what we learned in decision trees? What was the thing that we learned? Not the function. We didn't say anything about functions in decision trees. What did you say?
Branches.
The branches. So the questions that we ask and the order of them, right? And at the end, what are the decisions when we get to the leaves? These are the parameters of the model that we want to learn in decision trees. In perceptron, what we want to learn is the weights. What should be the weights so that we do well in classification? Okay? So the training is to find finding is about finding weights so that the training error is minimized. Of course, also paying attention to the error on testing data. Okay. So since we said that we want the error to be minimized, then this is an optimization problem. Okay. So we need to solve an optimization problem now. I want to get the weights so that the error on training and testing is minimized. Okay? Fine. And of course, this is, we'll not get into detail here. This is beyond the scope of this workshop. It's just enough for me that you know that this is an optimization problem. So there are ways to solve this problem and thus get the weights that we want, given that we have some training data. Now, it turned out that perceptron is a linear model. What do we mean by linear model? If I have a problem, very simple problem, that I want, let's say that you are getting into a machine learning course, and I want to predict whether you will pass or fail in the course before you're taking the course itself, for some reason. Okay? And I will ask about, or I will get two values. Okay? What was your score in programming course, and what is your score in calculus? And from that, I want to predict whether you will pass in machine learning or fail. Okay? Let's say that we got this data. And red here means fail, of course, red. Okay? So this one is passing, fail, pass. Okay? If that's the data now, then I can have a line that separates these two classes, right? I can have something like that, and this line now is perfectly distinguishing between the students who will pass and the students who will, or predicted to be, failing. Okay? Is that clear? We call this linearly separable data, because now we can separate the classes using a line. Of course, it is a line because we are talking about two features only. In higher dimensions, it will be hyperplane. Okay? But for simplicity, this is just with two features, it will be a line. Okay? So we call such kind of data linearly separable. And those types of problems, perceptron will be very good for them, because perceptron is about learning a line. Okay? It doesn't do well when we don't have such type of data. Okay? Now let's look at this instance of the problem. Let's say that this is the data. Can we separate them by a line? Are you sure?
We can, but you will have error.
We can have. Then we don't separate them.
We can't separate
Okay.
them.
We can. We cannot. What do you think? Okay, so we cannot, right? So this is called linearly inseparable or non-linearly separable. Okay, the same thing. Okay, so this data cannot be separated by a line. Perceptron cannot solve this problem. It can only solve such problems. Of course, we can try it, as someone of you said. We can try it, but we will not get very good accuracy. Okay? It's not guaranteed that it will get something good. But here, it is guaranteed.
But the graph itself doesn't make sense, like 50%, and then
We don't care about that now. Mukartum, I know that your way of thinking is much deeper than us, but that's fine. And I think, really, it makes sense, by the way. Because that means that if you are very good in programming, you will pass. If you are very good in calculus, you will pass. This one is a bit, but maybe this means that they are not very good in programming. Anyway, Mukartum, we can have an extended discussion with you later, okay? For the super students. I'm kidding, of course. You are super, but I'm okay. Anyway, so we'll not be able to separate this data, right? Okay, so they will not find a line. And by the way, this kind of problems is called XOR problem. You know XOR, right? So this is called XOR problem because if you put everything to 0 and 1, okay, you will move this to 0, this is here, this is here, this is here. It's like the function, the XOR function. If this is X and this is Y, then the function that we are trying to plot here is the XOR function. And for a long time, because perceptron was not able to solve this problem, the research on neural networks was slowed down a lot, okay? Because we could not really use perceptron to do this, to solve this problem. Now to try as a step or 2 steps to try to solve such problems, we'll do 2 things or 2 changes to perceptrons. Okay? The first one is to generalize the function that we have here. Instead of having always step function, we can use other functions that are nonlinear so that it will add nonlinearity to the model, and now it can work on linearly inseparable data. And there are many functions that are actually used now. One of them is called sigmoid function. I think you might be familiar with that in signal processing probably. Okay, so the sigmoid function takes any input and produces an output between 0 and 1. Okay, if the input is positive, then the output will be positive. As the input is very positive, the output will be 1. If the input is very negative, the output will be 0. So you can think of it as an approximation of what? Of something that we saw before, the step function. Okay? The only difference is that the step function is not differentiable, but this one is differentiable, and that makes a lot of sense and importance in the optimization problem. Okay? So this is one example of activation functions. By the way, we call this activation function now in general. Okay? We called the step function before, but now when we talk about neural networks, this function is called activation function. Okay? Still is. Do you have any questions? Okay. Still is applied after computing the weighted sum. Okay, as we did before. So the weighted sum will be calculated here, and then applying this function to the output of the weighted sum. Okay. And there are many other activation functions, of course. Sigmoid may be one of the popular ones, although now it was experimental proof that it is not the best. There are other activation functions that are actually much better than this, but this is a good example for now. By the way, this model, when we change the step function to be a sigmoid function, is called logistic regression. Okay? Because this function, by the way, is called the logic function, and that's why it's called logistic, and I don't know really why is it called regression. It has nothing to do with the regression, it is doing classification actually. Okay, but I don't know, I'm not the one who called it. It is called logistic regression in the literature, but it is actually a classifier. Okay? Now that was one step towards neural networks. The other step is now what we call now neural networks, is to combine some of these perceptrons together. Okay, so we started by just one neuron. Now talk about really many neurons connected together. So there are 3 things here. We will combine multiple perceptrons. Okay, we will combine them in layers. And you will see that some of the neurons, the output of some of the neurons, will be input to other neurons. Okay? And this is what we call neural networks. We'll see, of course, many examples now, but these are the basic concepts. We know perceptron will connect some of them together. How we will connect them? We connect them so that the output of one neuron is an input to the other neuron that is connected to, and we will structure these neurons in layers. Okay? What we mean by layer, you will see, inshallah, in the coming slides. By the way, we call sometimes neural networks are called multi-layer perceptron, and then I think now you understand why. There are multiple layers, and each layer, each neuron actually is a single perceptron. Okay? So sometimes you will see MLP when we talk about neural networks. So this is a perceptron, right? I just removed here the weights and biases for simplicity, but you can think of that as what we saw already before, which is one perceptron, right? So one perceptron is actually one layer neural network. Okay? And when we say layer, we are talking about layer of weights. Here we have one layer of weights, right? Each input feature has a weight to the single neuron. Okay? We call, and this is how we count the number of layers in a network, by the layers of weights. Okay? Because you might think that we have here 2 layers. But actually this is one layer of weight, and this is how we call, we name the neural networks. Okay? Here we have two different layers. Input layer, which are the input features that we saw before, and output layer, which has just one neuron now. Okay? So we can see one perceptron as a neural network, but it has just one layer, okay? One layer of weights, and it has one input layer and one output layer. Why do we call this input layer? Because that's the features, that's the values of the features of the input data, the training data that we will use. Okay? Always think about this training table that we saw in the decision tree example. Each column there was a feature. Okay, it presents a feature. So these are the input values, and that's why is that called output? Because the output of that neuron will be the output of the model, okay, of the network. Okay, so you would think that in any neural network, how many input layers and how many output layers? 1 and 1, right? We will have always one input layer and one output layer. Okay? Sometimes we'll have something in between. Okay?
Doctor,
Yes.
you just said in the outputs from one neuron will be inputs for the other.
That's in general, but now this network has just one neuron. So we still didn't see that yet. Okay? Any other questions? Okay. So this is 2-layer neural network. We have 2 layers now of weights. You see that the first layer, still input layer, it has every node is connected to the other nodes of the next layer. Okay? This is where we see connections between neurons now. Okay? So each one, these are the input layers. Of course, the input layers are not perceptrons, right? These are just values. But here we have 3 neurons, and here we have 1 neuron. Still, this is called output layer. Still, this is called input layer. And now anything in between is called hidden layer, because it's not seen. It's neither input nor output, so it is called hidden layer. Okay? Now every node here in this example, every input value is connected with a weight to the neurons of the hidden layer, and every node in the hidden layer is connected to the output layer. It's connected to the next layer, which happened to be the output layer here. And we have just one neuron in it. We can have multiple neurons, by the way. Okay? So any layer can have generally any number of neurons. And the connections is only between this layer to the next layer. You will not see in neural network connections between neurons in layer number, the first hidden layer and the third hidden layer. Okay? It's always connections between the neurons in that layer and the next layer. Okay? So this is called 2-layer neural network. Why is that? Yes, because it has 2 layers of weights. Although it actually has 3 layers. Input layer, output layer, and hidden layer. But when we call it 2-layer neural network because we have 2 layers of weights. Okay? Is that clear so far? Okay. Now, remember that each neuron is the same model that we discussed before in perceptron. Exactly the same model. Okay, it works exactly the same way. It has weighted sum, and this weighted sum is applied to the activation function. Okay, and the output of the activation function is the output of that neuron. Okay, so if that happens here, then this output goes where? Goes to the output neuron. Okay? Goes to the output neuron. But what happens here? And this neuron has 3 connections, right? So how, what, do we have one weight here or three weights?
3 bits.
3 weights. Each connection in the neural network has a separate weight. Okay? But how about the value of the input? Is it divided between the three
value.
connections?
No.
No, it's the same value. It's the same value copied through the 3 connections. It's actually modeling the neuron in brain. The theory says that the output of the neuron actually copied into the all connections. It's not distributed. It is actually copied. Okay? So that's what's happening here. So that's again two-layer neural network. Now this is in general multi-layer neural network. You see here that we have how many hidden layers here? 2 hidden layers. So we have 1 input layer, 2 hidden layers, and 1 output layer. And you can see that the connection now is getting more dense, right? It's getting more complicated now. Okay? Yes?
Is it possible to have a cascaded network?
Yes, of course. Yes, of course. Yes. The output of one can be the input to the other and so on. Yes. That's how it gets complicated nowadays. Other questions? Yes, sir.
In the reality, for the body, if we have the neuron in the body, the signal will be distorted.
I don't know. I'm not a biologist. I really don't know.
No, because I feel it mathematically it makes sense that the same value of the input must be copied to all others.
The theory says that, but we don't know if. I personally don't know.
Oh.
And that's beyond the discussion. Other questions? Should we move on? Okay. So this is the most common layer type, by the way, that it is fully connected. What do you mean by fully connected? Each neuron in one layer is connected to every neuron in the next layer. This is called fully connected. If that happens in every layer, this is called fully connected neural network. Sometimes you don't have to, by the way. And it's not a must. But that's the most common type. That we connect every neuron in one layer to every neuron in the next layer. Okay? Did you notice something else about the connections? And I said that there is no connection between this layer and that layer, for example, right?
Yeah.
It's always to the next. Did you notice if there are any connections between neurons in the same layer? No, there is no also connections between the neurons in the same layer. Whether this is representing what actually happens in the brain or not, I don't know. Okay, but that's how neural networks work. Okay, that we don't allow, at least in that type, we don't allow connections within neurons, between neurons within the same layer. We don't allow connections between neurons of one layer and more than one layer after. It's just connections between neighboring layers. Okay? So neurons within a single layer share no connections. Is that clear? Is that clear? Okay, now what is training? Again, I'm reminding you, if I have something like this, this network, what do we mean by training? We said it before, by the way. The weights, okay? So we want to find the weights which are on all of these connections so that this network will produce good output. It is not a straightforward problem, right? Because there are many values of the weights, we have many weights, so we need to find the optimal values for the weights so that this network will do the task that we want to do. Okay? And if it is that complicated on 3 layers, imagine that when we have even deeper networks with more layers. So many connections, right? Now imagine what happens in the brain. We cannot, or we cannot. Okay, now back to reality. So training is finding the best weights and biases, of course. and this is how these values are really tuned or found. This is beyond this workshop. It's a very long story. And the long story short, it is mix of two algorithms, one called back propagation and the other called gradient descent. And that's it about this in this workshop. Okay, so we'll not talk about how we train the network. We talked about how we train decision trees, right? It was really simple, but this one is not. Okay? That needs 2 or 3 weeks of lectures, not every day anymore. 3 weeks of teaching to do this. Okay, but prediction is really much easier. Okay, so we said always in machine learning we have 2 phases. We have training and prediction, right? So let's say that we train the network. What do we mean by training the network? We know the weights. Now we know the weights for the network. Okay, how can we do the prediction now? It's very easy. We go from the input layer to the output layer. Let's say that the input here was, we have 2 input here, right? 2 input features. Let's say that we have the values 1 and 1. Now we want to know what will be the prediction of this network. We'll do the calculation moving forward. So this one will be multiplied by the weights. Okay, this one will be multiplied by the weights. The sum will be given, will be computed. Okay, the weighted sum, and then going through the activation function, we'll get the activation value. Okay, here it's not -1 and 1. It seems like we are using something like sigmoid. Sigmoid is more smooth. Okay, so we can get some values like that. Now what happens moving forward? These values now are like these values, but for the next layer. Okay, so this value will be multiplied by this. This value will be multiplied by this weight. This value will be multiplied by this weight, sum, and then going through the activation function. So this is the sum of them, I guess. This is the weighted sum. And then after the weighted sum going through the activation function, we get this output. Now, how can we interpret this output? It depends on the test. Okay? If we are talking about classification, probably if it is positive or more than 0.5, we consider that positive class. If it's less, then we can consider that negative class. Okay? Is that clear how we do prediction here? So we get, what do we have in prediction? We have the example that we want to classify, for example, right? So the example is represented by features. That's all what we have, besides the model that we learned already, which is the weights. Okay? So we go from the input layer, computing all the values, okay, to this layer, and then the next layer, and then the next layer, until we reach the final layer. Yes?
Why don't you consider them all identical and they just have the same weights and have the same inputs?
Okay, but then we are not learning. This is the beauty of neural network, that by changing these weights, we learn something different.
I mean, they still have the same inputs. If you change the weights, then you can disrupt the whole network.
No. Okay. Why do you say that they should be identical? That might not be good for the task you have, right? It might not produce good results. But changing the weights and finding different values of weights might give you good results, right? So this is what we are learning in the training phase. Every task, I mean, let's say that we are using the same model of network, okay? But we can use it in different tasks. Using it in different tasks, what will be the difference? The weights that we learn in each task. Yeah, this network can learn, let's say, the age in the age prediction problem. Or it can distinguish between male and female in the image. The same same model, but we train the network now for different tasks. So we will get different weights. Okay? It's like what, assuming that this theory is really good, we have actually here probably multiple networks. One for, I'm just imagining now. It's like we have multiple neural networks, one for each task. One allows me to identify whether you are a student, identify whether you are male or female, for example. Okay. One for recognizing the voice. one to understand the words when I see them, and so on. Okay, all of these networks have different weights. That will make them different. And don't you think that we need a different network for every different task? We should. Okay, did I answer your question? Kind of. Okay, so that was prediction. Now let me ask you why, or ask. Let's think about that. Why would we want to do all of that? Why is that so complicated thing? Why should we care about all of this? Okay. So the answer is very simple once we understand this slide. So this slide says that machine learning is just function approximation. I think the term function approximation, you saw that before, right? Maybe numerical analysis or some math courses, right? When we have a function, we want to approximate it. Okay? You can think of machine learning as a function approximation. How is that? You saw this last time, right? Right?
Yes.
Okay. Now, if you remember, we said that we will have a learning algorithm, and we'll have data and desired output, and we produce a program. Okay? We can see that in a different way. Let's assume that the data and the output were generated by a function that maps the data to the desired output. So in reality, there is a function f that takes the data and produces the output for it. Okay, let's assume that we have this. If we assume that we have this, then what machine learning is doing is to try to find an approximation of that function. That's it. We are just trying to approximate that function. Okay? Of course, in many cases, we will not find exactly the function. Okay? But we will strive to find a good approximation function to the original function. Okay? That's why we call it h, not f. F is the original function. H is what you think was the program, but actually this is the function that we learned. Okay? And we hope that h is a good approximation to the original function f. Okay, did you get that? Okay. So now, after we learn h, this is the phase of prediction. We have h now. Let's get data and produce the output based on h or f. H, because we don't know f, right? We don't know f. That's what we want to get approximation for. Okay, we don't know f. We just saw some observations from f. So we want to approximate f, and this is what we got. We got h, now we use h. Okay, we call that program, we call that model, we call that function. All of these are actually the same thing. Okay, so now I hope that I convinced you, yeah, Shaykha, I think. Right? Shaykha, I convinced you that machine learning is just a function approximation. Type. How is that related to neural networks? One theory says that, and it is true, says that two-layer neural networks are universal function approximators. What does that mean? That means that you can approximate any function, using just two layers neural networks. If you have a neural network of two layers, you can approximate any function. That's what we mean by universal function. Universal. Any function can be approximated by just two layers of neural networks. Perfect tool, right? We don't know a function, but this theory says that any function, whatever the function is, you can approximate it by two layers only. A network of two layers. The one that you saw, I think, 2 or 3 slides before. We didn't finish yet. Question? Okay.
A good approximation or like a
Of course, we are talking about good approximation here. Yes. It doesn't have to be perfect, but it is good approximation. Okay. So that means that two-layer neural network can solve the XOR problem. You remember the problem before, right? It was just 1 point in every square here, but now we have many. Okay, so that's the generalization of the XOR problem. I told you that XOR problem was like a burden to perceptron. Perceptron was not able to solve this problem. Now, two-layer neural network can solve this problem easily. Easily. Okay? Fine. Here's another example. If we have this is the number of hidden neurons now. Remember, two-layer neurons two-layer neural network means that we have one hidden layer. Okay? If we have this problem, and we want to get a classifier with, this is the performance when we have 3 hidden layers, hidden neurons. This is when we have 6 hidden neurons, and this is when we have 20. As you see, with more neurons, then the network was able to get to be a good fit to the data. Okay?
Doctor, going back to the previous slide, you said that like it needs to be generalized.
Yeah. Good. Okay. So yes. Good that you noticed that. So we'll talk about that. Okay. Yes. Right. Now the question is, so you said that you want to say that, okay, this is bad. This is also bad because this is called overfitting. Good. Okay. This is overfitting. Okay. So keep that in mind. Now, if two-layer networks are so great, as the theory says, we said that the two-layer neural network, it can approximate any function. If it is that great, why do we care about deeper networks? Why should we have 3 layers or 4 layers or 5 layers if 2 are enough? We should not care about deep networks, right? We should not care about deep learning. Of course, we care now, as you hear. But why? If two-layer neural network is enough, why should we care about that? Okay. The key idea here is that I didn't tell you how many neurons in these 2 layers. Sometimes we might need infinite number of neurons in the 2 layers, or so many neurons in the 2 layers. Okay. But if you have deeper number of layers, you might have less number of neurons as overall, and you get better performance. Okay, or at least you learn much faster than the other one. Okay, so that's the key idea here. That we might require some problems or some functions might require huge number of hidden units. Although yes, we know that 2 layers you can do whatever you want, but we might need millions or maybe billions of neurons in each of these 2 layers to get what we want. Okay, and that's of course impractical. So in many cases, more layers is much faster. Okay, is much faster and getting also good results. Now, if deep is potentially so much better, why don't we always use deep networks then? So I convinced you first that 2-layer network is good. Okay, and then told you, no, it's not very good. Deeper networks are good. Okay, let's keep that and do deep networks only. As some of us think, we should only use deep learning. Deep learning is the hot topic. We should always use deep learning. Huh? We might have overfitting, and to avoid that, and this is back to your point, Shaykha, to avoid that, to avoid overfitting, we need a lot of data, of training data. And to really get deep, we need so many training examples so that we avoid overfitting. Okay? And because we need many examples, or the reason why we need many examples is that we will have, when we get deeper, we'll have so many weights, right? Sometimes even millions of weights. This is a lot, and it will take very much time to train. Okay? So these are the 2 things. Needs lots of training data, and also one thing also that we didn't mention. When you get deeper, how can we know how deeper we should go? How many layers? How many neurons in each layer? These are questions that might take us a lot of time to determine. Okay, so it's not always wise to have very small, shallow network, and it's not always wise to get very deep. Okay, so there must be something in between, right? Okay, so and by the way, finding good ways to train deep networks is a hot research topic, research area. There is a lot of research to know how to determine the number of layers and how to determine the number of nodes in each layer and so on. In practice, the wisdom here, okay, is go deep but not very deep. Okay? يعني in most cases 3 or 4 layers are enough. You should not go to 20 layers now because you want to show that your problem is very complicated. 20 layers of, no, you should try first 2 layers, 3 layers, 4 layers. You should not go beyond that in the beginning. Okay? In most cases, this is in practice the better than going deep from the beginning. Okay, so go deep but not very deep. This is a slide from Andrew Naimi's Coursera courses that shows why deep learning is exciting. It's really exciting. This is the performance, so here we are plotting amount of data versus performance. Okay? If you are talking about traditional machine learning algorithms, like decision trees, like perceptron, like logistic regression, then we can get a performance like that. After some amount of data, you'll see that the performance is almost constant. Doesn't matter if we add more data. Okay? This is with small neural network. We get a bit better when we have small neural network. We get even better with medium neural network, and with deep neural network we get even higher performance. Assuming that we have the computing power to train such networks. Okay? Many machines with GPUs and all of that. Okay? But given that we have the resources, deep neural networks are much more exciting because it's getting much better performance. And the most important thing is not just better performance, it is increasing with adding much more data, which we are sailing in now that we have data from everywhere. Videos, posts, audios, okay? So many things. Okay? Yes?
As a conclusion, then we have always to check how much data is available versus how much is the complexity that is allowed versus how much.
Yes, there are so many parameters. Yes, of course. It is an art.
Yeah, we should agree with Kulthum that it depends.
Yes, of course. I cannot disagree with I cannot disagree with Kulthum. She said it depends. It depends. Then it depends. Of course, it's not easy. It's not straightforward at all to know how deep the network is, how many layers, how many neurons in each layer. This is an art. Okay, and when you get experience, you get better in taking less time in doing that. Okay, quick advice. I think this is nice to see now. Okay, look at that. Wow. Did you get that? Okay, let me show it again. Very nice, right? Okay, what is the message here? Huh?
SDB project for next semester.
What is the message here? Do we really need this complicated door? It's just a door, right? It was open as we normally know. It's a door. We don't need that kind of complicated design, complicated model to solve this problem. This problem doesn't need a neural network, doesn't need deep learning. This problem can be solved by perceptron or by decision tree. Okay? So the idea here is what I think is written in the original post. This is when you use a 10-layer deep neural network where logistic regression would suffice. Logistic regression is just one neuron. Okay? So you don't need very complicated solutions for simple problems. You should always try to solve your problem with the simplest possible ways. Okay? Okay. This is the demo that I would leave you to to try. You can try some networks like this and see the output, how it changes with changing the layers. Okay, you can play with that. I will skip that. I think the time, if we have time at the end, we'll go back to this. So this is showing you in reality what are the stages to do a complete machine learning system. Okay, if we have time, after covering the rest of the talk, we'll go back to this. If not, then you will have the slide at least. It's just one slide. Okay, now the difference, I think this is important. Now, what is the difference between AI, ML, and DL? You hear a lot about artificial intelligence, you hear a lot about machine learning, and you hear a lot about deep learning. Okay, what are the differences between these? I hope that you understand now what machine learning is, to some extent. Come on, you didn't need to. Okay. So we need to understand the difference between these three things: AI, artificial intelligence, machine learning, and deep learning. What is the difference? So we'll take each one very briefly, very simply. We'll define each one. So AI is about developing techniques to enable computers to mimic human behavior. Anything, any software, any system that will try to mimic something that the human is doing, then this is artificial intelligence. We're trying to inject some intelligence into the system so that it does something that humans do. Okay? So examples: automate routine labor in factories. The robots that are connecting, putting something in a bag and moving the bag and all of that. This is kind of something that humans are doing, okay? But now it's mimicked by a robot. Okay, so that's kind of artificial intelligence. Of course, the robot is making some decisions sometimes. Okay, so it is mimicking human behavior. Understanding speech or images. That's AI, of course. Making diagnosis in medicine. Okay, looking at images of X-ray images and trying to predict whether this means there's a disease or not. Okay, or MRI images. So many applications. Okay, so anything, any system, any computer software or system that try to mimic human behavior, try to do something like human behavior, this is under artificial intelligence. Okay, is that clear? Right. Now the true challenge to AI is said to be solving tasks easy for people to perform, but hard for people also to describe formally. Yeah, for example, recognizing spoken words. Without putting any effort, we recognize what you mean by when you say words, right? Any word, we understand it, but we don't know how. Okay? So AI is meant, the main challenge is meant for that. For the things that we think it's very easy, very straightforward to do, we are doing without even thinking about them. Seeing, recognizing that we have chairs now and we have tables and we have humans and this is indoor and this is a class. All of these are things that we do for granted, right? We don't think of that. You don't enter the class saying that, oh, I really need to really think, focus to understand whether this is the table or not. Okay, we do these things for granted. So this is the main challenge to AI. Now, what is machine learning? Machine learning, as we saw before, developing techniques to enable computers to learn from experience. Okay, so that's the main thing here. So to try to learn from experience. I might build an AI system that doesn't learn from experience. It does some task, doing it exactly the same every day. Okay, but if you learn over time from experience, then this is machine learning. Okay. Now, is there any relation between AI and machine learning?
Yes.
What is the relation? Please don't answer. What is the relation between machine learning and AI? Yes.
Maybe artificial intelligence can be applied through machine learning.
Very good. Okay, so artificial intelligence can be applied through machine learning. You say you did it the hardest way. We can say machine learning is a branch of AI.
Yeah.
It's a branch of AI. So it is under AI. If you didn't notice that before, this is the time. Okay? So AI is a big umbrella. One branch of it is machine learning. So of course machine learning is doing AI. Okay? Because it's mimicking something that humans are doing, but through learning from experience. So AI, machine learning is a branch of AI. Now deep learning is developing techniques to enable computers to learn from experience. Up to this point, it is machine learning. And understand the world in terms of hierarchy of concepts. Okay? Hierarchy of concepts. There are two things here we want to discuss. So of course this is a branch of machine learning. Okay? This is under machine learning, but it's specific branch of machine learning. Now there are two things that we want to understand. There's something called representation learning, which means that we want computers to learn representations automatically. Yani instead of telling the machine that there is an edge, looking at images, there is an edge here, and there is a line here, and there is a contour here, or a corner here, or something like that. I want the machine itself to automatically generate these features, just by giving it the raw data. Okay, so before deep learning, we machine learning researchers and practitioners spend a lot of time in a phase called feature engineering, trying to extract features from data so that they can pass to the machine learning algorithm. With deep learning, we no longer need that, because there are techniques that can learn these representations automatically. And I will show you one example in the next slide. Okay? The next thing is that deep learning is not just representation learning. Here we say that we learn good features. Here we learn multiple levels of features, multiple levels of representations, okay, of increasing complexity. So it's more complex features. So here in representation learning in general, we learn features. Okay? In deep learning, we learn complex features by having a hierarchy of features or hierarchy of concepts. Okay? What does that mean? Look at this. Here we have a network that tries to detect whether this image is a car or a person or an animal. Okay? So this is the input layer. Now each layer here is trying to learn some features. This layer is trying to learn the edges in the image. This layer is trying to learn the corners and contours in the image. This layer trying to learn the parts in the three types of objects that we are trying to predict, and so on. So it's like a hierarchy of concepts. We start by learning concepts that are very, very simple, okay? And then from these simple features, we combine them to learn something more complex. Okay? That's actually what deep learning is about. Okay, so deep learning is not just a neural network, but it is, of course it is a neural network, but there are concepts that we were not able to do before that we can do. That we can automatically learn hierarchy of concepts. Okay? So instead of doing feature extraction, feature engineering in machine learning, now we let the network extract the features automatically. So we don't need to spend time on that. Deep AI, machine learning inside it, representation learning inside it, and inside representation learning is deep learning. Okay, I think this is very clear now. Okay, we still have 2 or 3 minutes. Let me show you one very nice demo. Maybe just one. So this demo is getting an image and tries to tell you something about that image. Okay, what is the category of that image, where it is captured, what are the objects in that image, and so on. Yeah, I tried it and it was really, really nice. So I will choose a file that has my son. Okay, an image that has my son. So that's the image, and it will tell you that this is indoor. And this is kindergarten classroom, which is 2. I was really amazed. to that it is really accurately identifying, recognizing that this is a kindergarten classroom. Okay, and what else? There is plastic, there is cloth. He's playing, probably competing with someone else. I don't know. Indoor lighting, and there is a paper. You see that? Okay. So let's try it with another file that I was also maybe this one. That's my other son. Okay. So do you guess? Can you guess where is that? In aquarium. Okay. And amazingly, it did. It says outdoor. Oh, it says aquarium. Oh yes, aquarium here. Yes. Really amazing. Really amazing that it says it detects that this is an aquarium, enclosed area. Of course, this is wrong. This is not outdoor. Okay, but it is any good enough. I think there is a class here, right? One more photo. This is what do you think is that? It's a mosque, right? Okay. Church. That's really good. That's really, of course it doesn't. Maybe it doesn't have example that says mosque, but that's pretty close. I will leave that to you. That there are some pointers for you to have more knowledge. You will see that there are resources for more background, okay, to increase your background for machine learning. You will have books, hands-on languages and libraries to use, okay, and online courses. Okay. I'll try to fill more links here, and even conferences if you want to look at research papers. And you need to practice, by the way, if you will be in this field, you need to practice. There is a website called Kaggle that has competitions, so I think you can practice also there. I think we got enough questions so far, right?
Thank you very much.
Thank you very much.
Thank you.